Okay, looks good. So I'll talk about, as promised, introduction to, well, simplicial distributions. Well, this will be an introduction, and well, just feel free to stop me anytime you want. And also, sorry for my voice. I've been sick for the couple of days, for the last couple of days. Now, so I just want to do a basic introduction and make connection to the theory of P-sheaves of distributions, which is more directly connected to the experiments that people do. And then I'll tell about simplicial distributions and how that generalizes sheaf theoretic approach to distributions. And then the goal here to understand there's this notion called contextuality. It's a property of distributions, but it manifests itself in quantum theory by violating the Bell inequality. So certain distributions, they violate Bell inequalities, and those are called contextual in physics. So the theory of simplicial distributions is an approach to describe that notion using algebraic topology. So let's start. I want to start with distributions. So we are interested in distributions on finite, like discrete distributions. So these are so a distribution is a function distribution on a set. Not necessarily finite, but you can think of it finite. I suppose for this talk it will be fine. Is a function to non-negative reals such that the sum is equal to 1. So therefore, the actual values are between 0 and 1. So here, U is going to have the interpretation of as being the set of outcomes. So you think of this as like an experiment. Could be like throwing a coin. The outcome will be 0, 1. So that's the set U. And you would have probabilities associated. If it's a fair coin, it would be 1 over 2, 1 over 2. So that's the function. And PU here is the probability of obtaining outcome U. Okay. So distributions have an additional property. So that's called marginalization. But for us, it will be a functor from the category of sets to the category of sets. So I already told you how to send a set to the distribution. So you just send U to du, d of u. But for a function, say between sets, you will go to a function between the corresponding distributions. And this function will send P, a distribution on U, to a distribution on V, such that the value at V, the probability at V, will be obtained by summing the PUs where U is in the preimage of V under the function of F. Function F. So essentially just think of the fibers of F, and you're summing these probabilities on these fibers to obtain the distribution on the target. So that's called the marginalization. So it's called DF. It's marginalization along F. You can say that. So it's a functor, and for us, important examples of such functions. Of course, any function would work, but for us, there will be 3 functions from Z mod D cross Z mod D. So here, Z mod D is just the group of integers mod D. So this is integers mod D under sum. This is an abelian group. So I'll use that structure. So there are 3 maps to Z mod D. So the first one is projection to the first coordinate. Second one is projection to the second coordinate, right? If I have a pair, I can go to one of those pairs. And the other one is, the middle one is the sum. If I have 2 numbers, I can sum them. So that will be the third function. So corresponding to these three functions, I can push forward or marginalize a distribution on a pair of distribution on the Z mod D cross Z mod D to a distribution on Z mod D. So I want to tell how that works. Of course, you can sit down and compute it using this formula. And I will just explain it for D is equal to 2 because it's simple and it's also more pictorial. So let me represent a distribution on Z mod 2 cross Z mod 2 as a box of 4 numbers. So these PABs are the values of the distribution on the pairs. If I have a distribution of Z mod 2 cross Z mod 2. So that's the notation I will use for probabilities. Now, if you project to the first coordinate, you will obtain a distribution. I will write for that distribution px0, px1. So I'm just labeling the coordinates. So this is the first coordinate, the second coordinate, x and y, just to distinguish them. So these two numbers, p0 and p1, will be obtained by summing these two numbers for p0 and these two numbers for p1. So this picture indicates how the marginalization works. So that's the push forward along this function projection 1. So let me do it here, projection 1. Now we can just do projection 2. So I need a clean box. Now that will be just the other direction, summing up these two numbers to obtain the distribution on Z mod 2, which is one of the second coordinate. So we have this P0 and P1 numbers. So this is a projection. So let me call this projection 2. So that's the second map. Now, for the final map, the sum map, the summation will go as follows. So I'll sum this diagonal and the other diagonal. The first diagonal will give me a distribution. So this one, the first diagonal, will give me a distribution. Of course, I have to label that too, right, in some way. And the label will be x plus y or x or y. So that's an operation, logical operation. And the other sum will be 1. So here, the first label is x and y, but just to distinguish the coordinates. But now x or here in this notation has actually a bit more meaning, operational meaning. So what is x or given x and y? So x, y are just, binary things, 0 or 1. So they can take 4 values, the pair. And x or is essentially the mod 2 sum. That's how it's defined. So we have 0, 1, 1, 0. So as you observe, the diagonal sum corresponds to the 0 outcome. So that will be the first and the last column, row. And the other diagonal will correspond to summing the other columns. Sorry, these are rows, yes. So we get these two probabilities. Okay. So these three maps will be important. So any questions at this point? How these maps are obtained? These probabilities are obtained. Okay, so this is the sum map, the third map. Right. Now, I want to talk about, so that's the basic thing about distribution. So we are using basically discrete distributions, and we want to marginalize them along functions. So that's the basic thing. So we are using this functor here, the distribution functor, as the basic object. Now, using that functor, we can consider more complicated situations. So here comes the pre-sheaves of distributions. So pre-sheaves are basically functors again on a certain category, and there's some additional data here that we need to consider. So the first one is something topological. In fact, it's a simplicial complex. And the second one is the outcomes. So as you see, Z mod D appears. So I'll just take Z mod D as the outcomes. So that's again outcomes from 0 to D minus 1. So I'm assuming here a situation where I perform an experiment and I have a set of measurements. So here, sigma 0, which will be the vertex set of sigma, will correspond to the set of all measurements. So for each vertex of the simplicial complex, I have a measurement. And these measurements, by choosing the second Z mod D, the second component, if I fix D, I assume that these measurements have D outcomes. So that's the scenario I have. So now, to get the pre-sheaves of distributions, we need a category that's obtained from the simplicial complex. So that's the sigma, it's the category. These objects are the simplices of the complex, and the morphisms are inclusions of simplices. Okay. So now on this category, I can define a functor which goes as follows. So C sigma, the set, and then sets. In fact, I'm just considering a composite functor here, composite of the two. So the first one will be this one, Z mod D, some sort of an exponential, and the other one will be the distributions. So the first one takes a simplex. Okay, maybe if you don't know about simplicial complexes, so the sigma consists of subsets. So these small sigmas are subsets of the vertex sets. Okay, and so this is essentially a set of vertices. And the first functor takes Z mod D to sigma, Z mod to the power sigma. So that's just a notation for functions from sigma to Z mod D. So I'll use this notation. It's a compact notation. Well, this is very similar to the notation we use in the course for the C to power sigma vector space. Is very similar. And then we can apply the D to this set. Okay. So the composite functor that goes from here to there, that's the functor we are interested in. Now, we can define a basic notion here, which is called an empirical model. So this part of the my talk is describing the work of Samson Abramsky and Brandenburger on sheaves of distributions for describing quantum contextuality and non-locality. So the basic notion they introduced is the empirical models. The element of limit of this functor, so which is this composite, are called empirical models. So if you know some basic category theory, you can tell what this set is supposed to be, this collection is supposed to be. So this consists of a family of distributions. And so let me say what these are. So these are distributions on Z mod to the power sigma indexed by the simplices such that for each inclusion, this is a morphism in the category C sigma, the distribution associated to C sigma, the smaller simplex, sorry, the larger simplex, restricts to sigma, gives us the distribution associated to the smaller simplex sigma. So here, this restriction is in fact something we already defined. So this restricted distribution is this is a shorthand notation for pushing forward the distribution P sigma. Sorry, sigma prime along the function which is obtained from I, but induced on this function set to this function set. Okay, so we had a distribution here, which is P prime sigma, and now we can push forward using the defunctor. Okay, so this encodes everything about this family of distributions. And these conditions here have special names. So these conditions here, this set of equations, here, they're called the non-signaling conditions. So this is like a physical name in physics for these distributions, these conditions. Okay, so these are called empirical models, these P's. And then there's a natural map that you can construct. So you can actually define some natural empirical models that come from distributions on the functions, set of functions from the set of vertices. So remember, sigma 0 is a set of vertices. That's all measurements to limit d z mod d. So this is the set of empirical models, right? All right, so I'll call this map theta. So how does that map work? Any ideas? How this map works? Well, okay, maybe it's a seminar, I shouldn't ask questions. But anyways, okay, I asked the question and I'll answer it. So let's see. Okay, so the definition here comes, right? So this is a limit, so it suffices to define maps to each of these pieces, and that comes from the induced map, right? So sigma is included in sigma 0, so you can actually map to those components. And then you have to check if it's compatible. Well, it's easy to check that. Recently, I had a lot of limit discussions, so therefore I just wanted to emphasize this. But anyway, so that's important. So it's part of the definition of empirical models. So this limit structure is essentially encoding the non-signaling conditions. Okay, so the basic definition now, which is important, and we studied this notion. So P empirical model is non-contextual if P is in the image of this map. Otherwise, P is contextual. I think this is one of the achievements of this paper, of this work, that it gives a very clear definition of some physical notion. So this contextuality generalizes Bell's non-locality. So this is a more famous name. Non-locality is very famous in quantum theory. It's taught in undergrad quantum physics, or the grad version, I don't remember. I remember learning about Bell inequalities in, I think I took a master's course here in my grad degree, I guess. So yeah, so they're very well known foundational objects in physics, and that's kind of like a more general version of it, and it's a very clear definition that uses category theory. Now, so what is the famous example here? And this is in fact a textbook example. This week on Thursday we will see it in class. So CHSH in class on quantum computation. So not everyone is in the class, but I know there are some people in the class. So this scenario we will learn on Thursday. So this is the simplicial complex. So this is in fact you can imagine it as a space, 4 vertices. It's a graph, right? 4 vertices, 4 edges. So this is our simplicial complex. Well, so what is CHSH? So this is the first letters of famous people. I think a couple of them earned Nobel Prize 2 years ago, a couple of years ago. So that's the simplicial complex. So I'm describing the scenario, and the outcomes in this scenario is Z mod 2. So D is equal to 2. So let's name these vertices x0, x1, y0, y1. Okay. Now, so I have to imagine this simplicial complex as a category, C sigma. Maybe I can just make a quick picture of that category. So it's really small. So I have x0, y0, one of the edges. The other edge is y0, x1. The other edge, x1, y1. And the fourth edge is x0, y1. Okay. So each of these are the maximal simplices, and they also intersect. So let me draw that poset here. So there's an intersection like this, containing x0. There's an intersection here, y0, here, x1, here, y1. So these are the 4 intersections corresponding to the vertices. And that's it. That's the picture of C sigma. So these are inclusions this way. Okay. Now, what is an empirical model here? Right? Say, if I had only x0, y0, so if I had this edge only in my simplicial complex, I could actually talk about what the empirical model is, right? So the empirical model in that case would be just a distribution on Z mod 2 cross Z mod 2, right? So I could just represent it as a box, as in the previous case. So these are 2 measurements, and we have 2 outcomes. So that's an empirical model in this case. Well, if you notice, there's nothing to compute in the inverse limit, so the maximal thing would be the inverse, or maximal thing would be the limit. So in this case, we have actually 4 of these things, 4 maximal things. So for each of them, we will have a box. Of course, I have to remember the intersections, and more importantly, how the marginals go. So maybe I'll just do one more layer on this picture, which is the functions. So remember that the first part of the function is going to take me to functor, is going to take me to these functions, function sets. So for each of them, we will have these function sets. X0, Y1, okay? And then here, X0, Z mod 2, Y0, Z mod 2, X1, Z mod 2, Y1. So this is contravariant. The arrows will go in the other direction. So I have to be careful. I just invert all the arrow. Okay. And then I'll apply the distribution functor. So I imagine there's a D in front here, everything. And then compute the marginals. So we already did compute the marginals. So these are projections to the first and the second coordinate for each case. So we did this computation already. So it turns out, if you put it on a box, it turns out that these 4 distributions in these boxes, the way I labeled them, maybe I should tell you how I labeled them. So here, for example, I can take, so the sides, this is x0, x1, y0, y1. So each pair is going to be the pair of the box, right? The pair of labels that correspond to maximal simplex for the box. And the null signaling is going to be precisely the matching of the marginals, right? It will look like as follows. If I choose a column or row, then say I just choose this first column. The two numbers here is going to sum to the same thing, so they will match. Similarly here, and similarly here. So for each column, the two numbers on top with the two numbers at the bottom is going to give you the same number. And we have, so this is one direction of the marginals, and the other marginals are going to be the matching of these two numbers, summing up to the same thing, and also these two, these two, these two. So this is all the non-signaling relations here. So a valid distribution here that satisfies these conditions is this one, for example, 1 over 2, 1 over 2, 0, 0, 1 over 2, 1 over 2, 0, 0, 1 over 2, 1 over 2, 0, 0, 0, 0, 1 over 2, 1 over 2. So you can check that the conditions I told you, they all give you 1 over 2, so they actually match. Okay, any questions so far? Okay, so yeah, so these are empirical models on the CHS8 scenario, a very important scenario in physics. And there's a corresponding theorem that physicists proved, like in 80s. P is non-contextual. If and only if, so say, okay, I don't mean that particular one, but empirical model in this scenario. If and only if the following inequalities are satisfied. So now we will need the XOR marginalization. So if you remember the definition of this thing, so this is the boxes, right? You need to sum the boxes, the diagonals, the diagonals of the boxes to get these distributions. So I just need the zeros for these distributions. So for each box, essentially we are summing the diagonal that goes from left to right. But there is one minus here. The rest is plus, so I want to emphasize that. So this expression is between 0 and 2. But there are actually 4 copies of that. So it's very lucky to give this presentation on Zoom. It's very nice to duplicate these things. So I'm even lazy, I'll just do this. Okay, so this one goes up here, but I need an additional plus. All right, so the location of the minus just slides, right? It just goes from one end to the other end. So we have these inequalities. So these inequalities have a name. So they're called CHSH inequalities. And on Thursday, we will see this theorem, and I'll prove one direction, this one. The other direction is hard, but the other direction is due to find. And, well, I can say the one goal of the theory of simplicial distributions is to provide proofs for these harder directions using topological arguments. And actually, we will do this for Fein's theorem, even for harder, more complicated scenarios. In the next talk, I think Salman is going to talk about that. This is one problem that we try to solve in simplicial distribution. So that's the identification of Bell inequalities. So these are examples of Bell inequalities. And the other type of question is to identify the extremal distributions. So that's the second type of problem. And Aziz is going to talk about these kind of problems, I think, in the 4th talk or so. Again, these two types of problems, they're dual in nature. So they are fundamental problems in polytope theory. One of them is called vertex enumeration. The other one is facet enumeration, and they are dual. They are very hard problems in general, hard in the complex sense. So we will see some of them being solved using algebraic topology, using the theory of simplicial distributions. So now I can talk about simplicial distributions, introduce them, and show how sheaf theory actually embeds in it. All right, any questions before I move?
I have one question.
Okay.
So I think I missed a point. So isn't those P's are probabilities? I think in for example, Fine's theorem, this less than or equal to 2 thing is expectation, sum of the expectations.
Yeah, good point. Actually, yeah, it's a very good point. So there are two ways you can write down these equations. So yeah, I think it's a very good point. So usually in physicists don't write it this way. So that's probably why you're surprised. So there is this following relation. So I can define, so for any measurement x, it's an any label of measurements. It could be x or just any measurement. So I can define the following thing. So there's something called the expectation, right, for that measurement outcome, which I can define to be P0x minus P1x, right? So, and also, of course, I know P1x is equal to 1 minus P0x. So what is that going to be is 2 P0x minus 1. So I can express these expectations in terms of P0x's. So you can in here, you can replace these P0s with the corresponding expectations, just change these P0x's with the corresponding expectations using this definition. Then you will obtain the original form of the CHSH inequals. And in fact, that's the one we will see in class. Yeah, so that's a good point. Working with expectations is a bit more nicer in some cases. Yeah, so that's the connection. Any other questions? Okay. Yeah, so let's move on to simplicial distributions. Okay, so we haven't seen any topology so far. Well, we have seen simplicial complexes there, topological objects. Now we will see an object called the simplicial set. So it's like fast forward in the history of algebraic topology, many years, and well, hopefully I'm not saying anything wrong. Hopefully, simplicial sets are discovered after simplicial complexes. I mean, logically, I think they are, but I'm not 100% sure. Okay, so simplicial set consists of x0, x1, x1 up to xn. Sorry. So these are sets indexed by natural numbers. So these are, so xn stands for the set of n simplices. So there are structure maps here, space maps, that go from xn to xn minus 1, denoted by di, and degeneracy maps, xn to xn plus 1 sj. Yeah, so if you haven't seen any simplicial sets before, I know most of us have seen that. They are very similar to simplicial complexes, except that you can do more collapsing, more gluing, and then capture any topological space up to homotopy. So that they're very powerful, invented by Dan Kahn. So very elegant objects. You can think of them as like, combinatorial descriptions of any space up to homotopy. Of course, there is something I'm hiding here. There's simplicial identities. The SJs and the DIs are supposed to satisfy them. And there's a sub-index IJ, there for any fixed n, there are a couple of those maps. I think they only make sense on the pictures. I'm not going to spend so much time on simplicial sets. I'm kind of assuming that they're known. But if you have any questions, I can try to clarify. So I can just say maybe a bit more. The face maps encode what things are supposed to be glued, and the degeneracies just encode what things are supposed to be collapsed within these sets of simplices. So at this point, the sets of simplices, they don't see each other, and you have to identify some of them, that's glue them, and some of them are supposed to be collapsed to get an actual topological space. But anyways, so we're mostly interested in these two structures, the face maps, which will be encoding the non-signaling. Okay, so let's see how much I will say about that. So a simplicial set map, that's the second thing. A simplicial set map between two simplicial sets, x, y, consists of functions indexed by natural numbers. Again, compatible with the simplicial structure. That's essentially these identities. Okay, so I am just hiding these details because it will take a lot of time to go through. But anyway, so I'll try to give more intuition, hopefully, as we go on. Now, finally, I can come to the definition of a simplicial distribution. A simplicial distribution is a simplicial set map that goes from x to dy. Yeah, it's a very, very compact object. So it encodes a lot of things. So this dy here is a simplicial set whose n simplices are given by distributions on the n simplices of y. And of course, we have to define these structures, the faces for dy and the degeneracies for dy, and they are defined as the push forward of the faces of y along the d functor, using the d functor, and then the degeneracies of y. Okay, so we are using that, the d is a functor here. We can also see simplicial sets as functors. Well, technically we can see everything as functors here. But yeah, okay, so I'm not going to go into that. It's the best way to approach, but yeah, this takes a bit more time. So now, having introduced these simplicial distributions, of course, we don't know what they are yet. So they're just some simplicial set maps of this form. Of course, everything is happening here. We can define in the same manner. Sorry. So there's a natural map that goes from distributions on simplicial set maps from x to y to simplicial set maps from x to dy. So the target is, as we defined it, the set of simplicial distributions. Like, just remember the analogies. I just remind you more clearly, because this is also called the theta map. So like in the empirical models, we have something here, and we want to send to something in the target. But this time it's a simplicial distribution in the target, and the thing in the domain is a probabilistic distribution on simplicial set maps. So I can think of this D as, say, just assigning probability values to simplicial set maps. Well, anyways, I'll just write it more clearly maybe now. Say, how do I define this one? So that's the thing I need to define. Given D, P is going to be defined as follows. So P is a simplicial set map. So that means if I take a simplex here, and in simplex, I need to send it to a distribution on the n simplices of y. So this P sigma thing is going to be accepting values theta from the n simplices of y. And we define it as follows. It's quite a natural formula. It's ds. Okay, so I'm using this d here, probability values. And S is here a simplicial set map such that S sends sigma. Okay, I'm using this similar notation. So sigma goes to something in the target, P sub sigma, or S sub sigma if the map is S, such that this goes to the simplex theta. So maybe I should say what this thing is. So this is defined as Sn of sigma. Okay, yeah, I like this notation. All right, so that's the definition of theta map. Of course, some things are happening here, not so clear. How do you, combine these distributions into a distribution? A simplicial distribution so this is kind of, if you just sit down, this is the most natural way to do it. And that's the theta map in simplicial distribution. So now given this map, of course, we can define P, a simplicial distribution this time, is non-contextual if P is in the image of theta, and otherwise P is contextual. Exact same definition as in the shift theta case, of course, with a different theta map. So initially I was planning to give some small examples, but I realized that I won't be able to make it in time. So I won't give small examples. Instead, I give a example or the case of P-sheaves embedded here, because I usually talk about this small example triangle whenever I talk about simplicial. I always draw that picture. That's the fundamental picture. It requires nerve spaces. So yeah, I'll just do a different thing this time. So I'll describe the embedding because that was the goal of the talk. Empirical models, or P-sheaves of distributions into simplicial distribution. So now, how do you embed something? Well, what is the data in the sheaf structure? Well, we have a simplicial complex and the outcome Z mod T. Now, in simplicial sets or simplicial distributions, we have a space of measurements X and space of outcomes Y. So we have to define X and Y. So let's start with the Y, outcome space. So I have to construct something from sigma and delta Z mod T, an outcome space. So the notation will be this one. So what is this? So let me tell you what the n simplices are. So they are kind of the simplest thing you can do given the outcome Z mod T. So you don't have much. Well, you can just take the n plus first power of the Z mod T. So n plus 1 tuples. And then you have to tell what the face maps, say, given this n plus 1 tuple, the face map will omit the ith index, ith element, so you get an n tuple. And the jth one, the jth degeneracy will duplicate the jth element. So aj, and then you duplicate it. And then the rest is the same as before. So you have a tuple of size plus 1. Plus 1 before one more than the earlier. So these are the structures. So you specify the simplicial set exactly. And X again here is the measurement space. So let me define it too. I'll write X sigma because it will come from sigma. So the construction is quite similar to this previous one. So I need to tell what the n simplices are. And these are, again, n plus 1 tuples, but this time from the vertex set of the complex. And we are not taking everything because we have to remember the simplices of the simplicial complex. So we are taking those where these things are, in fact, form a simplex of the complex, original one. And I will even restrict to ordered simplicial complex. So I haven't talked about it, but you can also order the vertices of a simplicial complex that will give you a ordered complex. This simplifies things, so that will be the assumption. I guess in my earlier picture of the circle, you should add orientations to the edges. So you have to pick some orientation. That simplifies things. Now, so I've specified the data here, but now, of course, given an empirical model, given P, an empirical model, so we want to define a simplicial distribution. So let me call it P tilde from the measurement space that we constructed to the outcome distributions on the outcome space. So how do we define this? Well, so what are we supposed to do? So we need to take a simplex here, take an n simplex, and then we need to send it to a distribution indexed by the simplex. And the distribution is supposed to accept n plus 1 tuples of z mod d. So essentially, so this p tilde x0 xn is going to accept a0 an as an input, and well, just remove these parentheses and replace them with something more relevant in empirical models. Well, we just turn into sets, right? For example, I can take the tuple, form the simplex, and I can take these n plus 1 tuples of outcomes and then turn it into a function that assigns as xi's to si. So I can evaluate, remember, empirical models on functions. So s is a function here. That's the formula. Of course, you have to check that it's a simplicial Z map and so on. There's a lot of verification that you have to do. They're easy, so I'm just skipping them. So this gives a function from distributions on. Sorry. So this is a notation which I haven't introduced. So this is maybe I should write distributions, but okay. This is in fact a set of empirical models. So this is a notation I forgot to introduce. And this goes to now simplicial distributions. I think I didn't also introduce this notation. Okay. So the nice property is the following. P is contextual. That's something you would hope, right? If you want to embed something meaningfully, P tilde is contextual. So the left-hand side in sheaf theory and the right-hand side is simplicial. Okay. So that's it. So that ends the main part that I wanted to achieve, which is embedding sheaf theory into simplicial distributions. Yeah, so you have to pick these measurement space and outcome space properly to do that. And then the notion of contextuality for simplicial distributions actually coincide with the one for p-sheaves of distribution for empirical models. So let me see. There's one more thing I want to do. Of course, one could, again, look at the CHSH example. But this is not the usual picture I draw for the CHSH example because I work with the the triangle picture. This is one-dimensional lower, so this is just a circle again. So this is the simplicial set for X sigma, where sigma is the simplicial complex which looks like the same. So remember that when we analyzed empirical models, we looked at one edge and constructed a box out of it. And then we understand how they match. So here in the simplicial world, what you would need to do is to start from understanding simplicial set maps from delta 1, which is the one simplex, to distributions on this outcome space. So what is that supposed to be? So it's not hard that this actually also corresponds to a box in the same way. So if I take the delta 1 has an important simplex, so that's we call the generating simplex in degree 1. So that will, let's call it sigma, there's a unique one. It will go to p sigma, which is a distribution on z mod 2 square, so z mod d square. So remember that the simplices of delta z mod d in degree 1 are pairs of elements of z mod d. So that's precisely a box, right? If d is equal to 2. So let me do it for d is equal to 2. And what do I need to compute to be able to understand if I have 2 edges and 3 edges and 4 edges? So I need to understand this distribution right here. How does that marginalize to the vertices? So in other words, I need to find a distribution for d0 sigma. So if I put this orientation, this one, remember I need to choose one. So this is d0 sigma, this is d1 sigma, the vertex. So since P is a simplicial set map, d0 comes out, it commutes with P. And in my notation, that's how you write it. Well, this is not standard in simplicial sets. So this corresponds to, if you compute it, using unraveled definition, so you would actually get the marginalization, which is precisely to the left-hand side of the box, right? And if you do the D1 phase, this will give you marginalization to the top part of the box. Okay. So now you can have the other edges and so on. You have 4 edges, and you have this marginalization relation. That will exactly reproduce the same marginal relations for, or non-signaling relations for the CHSH scenario, that this big 4 boxes. So maybe I should just, so this is sigma here. Maybe I'll just call this tau, this simplex, and then give the orientation, say this way. So then the same vertex, if I look at this edge on the left, will be d0 tau. So they are the same. So I should have, for example, the following marginal equation. So dp sigma marginalized along d1 is supposed to be the same as p, sorry, this is still d0 of p tau. So the marginal equations start to look like this. And these, well, a couple of those, of course. So these are, you can call them as, the topological non-signaling conditions. Well, they're in fact richer than the ones that you can obtain in sheaf theory because of the weird gluings you can do. But remember that we're just looking at a one-dimensional space here. Well, you can have arbitrary spaces. So it's the theory is very, very general. Of course, we will see different kinds of examples throughout the talks. And well, I usually talk about triangles, and this time I just talked about this one-dimensional lowercase because of time constraints. But I think I will end here. Any questions? Okay.
I have a question.
Yes. Right.
So in the beginning, you defined empirical models as an inverse limit, right, of the composite functor. So we are taking this limit on the in the category of categories, I guess. So how do we get a set actually? So
no. We're taking the limit. So the functor is going here to set. Right. So we're going to obtain a set. Yeah. It's not complicated. It's just everything happens in the level of sets. Yeah.
Okay, good.
Yeah, so these are actually, I call compatible, but yeah, so just functions which are compatible under some relations. That's what essentially an inverse limit is, if you ask, in the category of sets. So that's why, usually people don't write it's an inverse limit because, it might cause some confusion just using something abstract here instead of saying what it is exactly. So it's exactly this with that conditions. Yeah. But I think it's kind of instructive to think about as a limit because you could do something similar for simplicial distributions, right? So you can write it as a limit 2 if you decompose X into simplices. So it has a similar structure in that sense. But anyway, so this limit essentially, I mean, this diagram can get very complicated and you can't really work it out. So that's the main thing. So if just a circle here, the diagram is actually a bit big, and you might have something much complicated. I mean, for example, the other kind of scenarios that we will consider, they're called the cycle scenarios, which is just a straightforward translation of this type of scenario. So instead of 4 edges, you can have n edges, right? Like this. And so on. So this is a cycle scenario. And of course, the category will expand to the sides, right? And how are you going to show something is contextual, non-contextual? The goal here is, when we say that, we want to understand these inequalities, right? So you find a set of inequalities which guarantees something is non-contextual. Okay, so in this talk, I haven't mentioned any quantum theory, but we will also do that in the upcoming talks and the lecture on Thursday. We will actually try to violate these things from using distributions that come from quantum theory. That's the natural way of describing them. By the way, this distribution here, the one I wrote, is kind of like the simplest one you can write down if you just try to match these inequality, the non-signaling conditions. So this has a name. So this is one of the PR boxes. So these are not realizable as quantum distributions. So they are classical, but even outside the quantum distributions, they're very, very, very non-classical. So this is a vertex of the CHSH, the simplicial distributions, or the distributions of empirical models. That's also a polytrope extreme point. Okay, I think Aziz will talk about them next time. Any other questions? Okay, so if not, let's end here.